We are Group EIM 308, and our project aims to design a method to provide quantifiable pressure data to assist prosthetists in designing prosthetics. Did you know 85% of major amputations are caused by foot ulcers, which are commonly found in diabetic patients? Globally, in every 30 seconds, one person will require amputation due to a diabetes-related complication. With 1 in 9 Singaporeans contracting diabetes, this problem is becoming much more prevalent. Sam is a type 2 diabetes patient. She was just informed by her doctor that she requires lower limb amputation below her knee due to foot ulcers in her foot. After amputation, Sam had a tough time integrating back into society and the workforce due to the loss of mobility. Feeling depressed, Sam decided to go to a prosthetist, Dr. Steve, to seek help in fitting a prosthetic. After Dr. Steve fitted Sam with a prosthetic, Sam felt much more confident of herself and is able to work normally. She used a prosthetic for extended periods every day, up to even 12 hours on certain days. However, after a few weeks, she felt that the prosthetic is uncomfortable as it is not fitting her residual limb well. She has been facing problems such as abrasion and even blisters at the stump in contact with the prosthetic. Despite going back to alter her prosthetic with Dr. Steve, Sam faces the same problem repeatedly, where she discovers that certain parts of the sockets are not fitting well with her stump. Steve has been working in the prosthetics industry for almost 10 years, and he acknowledges that the problem Sam faces is common among amputees. Steve has to rely slowly on the subjective opinions of his patients on the level of comfort with prosthetics to make necessary adjustments, which is often not reliable. Over time, he discovers that he lacks quantifiable means to obtain feedback data during his prosthetic fitting sessions, which will help him in designing a socket which fits comfortably on his patient's residual limbs. This problem is not faced by Sam and Steve alone. Singapore has one of the highest rates of lower body amputations, with public hospitals here needing to conduct some 4 amputation procedures a day. Currently, although 84% of amputees choose to wear prosthetics, 1/3 of amputees are not satisfied with their prosthetics due to poor socket fitting. In order to find out more about the problem, we interviewed Dr. Trevor Binadell, a prosthetist at Tan Tock Seng Hospital. He shared that special care has to be taken with the socket as it holds the patient's stump. The socket is the most important part, and when the socket is uncomfortable, patients are unlikely to wear the prosthetic. Therefore, prosthetic need to be customized to suit each patient. He also mentioned that if quantitative pressure data can be obtained, it will help him assess the socket fit and aid him in creating better fitting sockets. From our research and interviews, we identified our 2 main stakeholders' needs. For transvertebral amputees, they need personalized prosthetics with optimal fit because inaccurately modeled prosthetic fittings can create avoidable problems. Whereas for prosthetists, they need a sensor system capable of providing pressure data because the pressure data is necessary for improving the design of personalized prosthetics. Moreover, the data recorded is unique to each patient's movement pattern. Through further interviews with Dr. Trevor, we found out that apart from quantifiable data, there are certain demands and requirements that have to be met. 1. Sensing system must be small in size. 2. Sensing system needs to model after different limb shapes and sizes. 3. Data of 3 specific locations as stipulated are needed. These areas are where the pressure is the highest. 4. Sensing system needs to be comfortable. 5. Sensing system needs to be sanitizable. 6. The sensing system must be durable. Several existing solutions are available in the market to prosthetists. One popular example is the F-scan system, which provides detailed pressure profiles and graphical displays for quantitative analysis. However, there are certain limitations of F-scan. Firstly, it is not very flexible. Secondly, it is attached to the prosthetics and not the residual limb. This results in certain areas not being in contact with the stump, leading to inaccuracies in the measuring process. Therefore, we decided to design a sensor that could gather quantifiable pressure data and fit the demands of prosthetists while working around the limitations of current solutions. In coming up with our solution, we considered 4 different types of sensors, namely direct loading, hydraulic load cells, pneumatic load cells, and springs. We came up with 20 unique concepts to address the prostheticist's needs. To evaluate the different concepts, we came up with the following 8 selection criteria. 1. Accuracy. 2. User-friendliness. 3. Comfortability. 4. Ease of data handling. 5. Durability. 6. Portability. 7. Manufacturing ease. And lastly, load handling. Based on the selection criteria as shown, we have selected our top 5 concepts which we will be further evaluating. Concept 1 consists of pressure sensor cells arranged in a huge matrix across the entire substrate. Pressure is measured at multiple points to obtain a pressure map captured in real time. Concept 2 uses a hydraulic load cell along with piezoresistive pressure sensing method. Concept 3 is a huge matrix of small 5x5 mm hard circuit boards that are interconnected with electrical wires. This allows for transverse and axial motion relative to one another. Concept 4 shows a pneumatic load cell used in tandem with a micro-electro-mechanical pressure-based sensor and a piezoresistive pressure sensor. Concept 5 shows pressure sensor cells that are arranged in a 2x3 matrix encased within a flexible substrate. This substrate is roughly 3x3 by 1 cm in size and is also water resistant. Having evaluated the pros and cons of the top 5 concepts, Concept 5 was ranked the highest and hence we decided to further develop it. Our envisioned final product aims to address the problems faced by our stakeholders. To reiterate, our product is designed to provide accurate and quantifiable pressure readings to prostheticists to aid them in designing personalized prosthetics for their patients. After considering the design requirements and the limitations of current solutions, we came up with a possible solution which was inspired by Concept 5, a 3x3 by 1 cm patch of sensor system made from a stretchable substrate with the ability to measure pressure at specific locations. At the same time, our product should be durable and easily sanitized. The small sensor patch consists of pressure sensors enclosed in a stretchable substrate. Each pressure sensing patch consists of 6 different pressure sensors, which will be connected within the circuit shown and calibrated to obtain pressure data. This is an illustration of the flexible substrate. When the sensor patch is placed between the patient's thumb and the prosthetic socket, pressure data obtained will be transmitted through an Arduino microcontroller and onto the laptop display. We are then able to see a pressure against time graph that is to represent the data from the loading. Upon having an envisioned final product in mind, we have identified and completed certain stepping stones towards developing our final product. Prototype 1 is a blinking LED circuit. This is a proof of concept where we created a sequential code via Arduino to make the LEDs blink at given intervals. The microcontroller receives an analog voltage and transmits it onto a monitor. Using the voltage divider rule, we are able to measure the voltage across the LEDs, which would then be replaced by piezoelectric pressure sensors, which would then be calibrated to give pressure data. Next, we experimented with the Cham-Hai pick-and-place machine for PCB assembly. Although it may seem irrelevant at the moment, pick-and-place machines will come in handy in our future prototypes where we will be working with very small electrical components that are difficult to assemble using our hands. Using the machine's position calibrations and auto-detect mechanism, we can automate the production process of our final pressure sensor. Recently, we had also completed our load cell prototype, which is an upscale method of measuring pressure data using a 10 kg load cell. This upscale prototype has proven our ability of utilizing a piezoelectric pressure sensor to reflect loading data in kilograms on a monitor upon adding load onto the load cell. This is the schematic diagram of our final product. With the help of CADing softwares, this is the computer-aided design of our envisioned final product with the circuitry embedded within it. Here, we can see how the substrate would appear with and without loading conditions. We look forward to developing our proposed concept and having it tested out with our partner prostheticist, Dr. Trevor, who will give us the relevant feedback to improve on further iterations. Thank you.